magnitude. To move further and to study the molecular spectroscopy, especially we will use a diatomic molecule. And in diatomic molecule, we will see that how the rotational spectra, or how the vibrational spectra and rotational vibrational as well as electronic spectra of a molecule appear. What are the energy level separations, and what are the different features of these spectra, that we will study. But before that, before we study the molecular spectra in detail, it is important to know that we will be using an approximations. We'll be using various approximations actually, not a one approximation. And the first and the important among them is Born-Opphenmier approximation. So to simplify the understanding of molecular spectra, Born-Opphenmier, they presented a quantum mechanical equivalent of this approximation. So they showed that the molecular Schrödinger equation, because in atomic spectra we solved the Schrödinger equation for an atom, for a hydrogen atom, but in case of molecules, the molecular Schrödinger equation can be solved in 2 steps. So Born and Opphenmier, what they did, they presented actually, they gave us presented quantum mechanical equivalent of the approximation what the approximation is actually. The approximation is that motion of
electronic motion
of the electrons at any instant of time is same as if the nuclei are fixed. So they assume that the nuclei are fixed in a molecule. This was the approximation actually. So they gave a quantum mechanical treatment of this. They quantum mechanically derived an expression in which they put up the approximation and derived the result from this. So how did they do it? We will derive that. We will see that in this class. And another point was that to derive this, to use this approximation and to derive a result out of this approximation, they showed that the molecular Schrödinger equation can be solved in 2 steps. So how we solve it? Now see. So keep in mind that we are assuming that the nuclei are fixed. We are assuming that in this approximation. And when they are fixed, so what will happen? The wave equation for the electronic motion alone, independent motion of electrons, is first solved, in which nuclear coordinates simply appear as parameters because it's not varying. So they appear as simple parameters. Number one, that means we first find out the wave function for the electrons of a molecule and keep the nuclear wave function as a parameter in that. Number second, remember that we have to find the wave equation of a molecule, not an individual electron or an individual atom, individual nuclei. We have to combinedly find the wave equation. So the second point is then the wave equation for the motion of nuclei alone independently. So it does not affect actually the wave equation of an electron alone. These are just simple steps which will be used to find the final expression, final Schrodinger equation. Alone is solved. In which the characteristic eigenvalue means energies, eigenvalues of electrons or electronic equation as part of the potential energy function. Potential energy function of the nuclear motion. That means the electrons will be treated as a potential for the nuclei. So the characteristic eigenvalue equation of electrons that will occur as part of the potential energy function that we will see in the below in the steps. So these are just two steps. You can go through this step again to understand it properly. The wave equation for the motion of nuclei alone. It is solved by considering that the electronic wave function, electronic eigenvalue characteristic eigenvalue equation that acts as a perturbation, or sorry, the potential energy term in the nuclear wave function. How? Let us see it. Number first, let us start. So we know that H, the Hamiltonian operator in general, is minus h cut square divided by 2m del square plus v. This is a general Hamiltonian. Let us suppose that it is for a molecule, for a whole molecule. Suppose that this is a general equation of an Hamiltonian. A general representation of an Hamiltonian. For a molecule consisting of alpha nuclei, having alpha nuclei, 1, 2, 3, 4, 5, 6, n equal to alpha. So it has n alpha nuclei, and it contains I electrons. This Hamiltonian can be written as, how we will write it, minus summation of, because we have now alpha nuclei and I electrons, so we will use a summation of h cut square by 2m alpha, first for the nucleus. Okay, and it is del square alpha minus summation of I over electrons, h cut square divided by 2mi, like we have m alpha, we have mi here, delta I square. Now take the potential terms. This is the kinetic energy part. Let us take the potential energy part. It will be for nuclear nucleus, for nucleus electron, so is it okay?
Yes, sir.
Let this be first.
Yes, sir.
Now, this is a kinetic energy term operator actually for all the nuclei with masses m, m1, m2, m3, m4, m5 up to m alpha. This represents the kinetic energy term for all electrons. First electron, second electron, third, fourth, fifth. How many electrons there are? Let this be I electrons. So I electrons. And this corresponds to the potential energy function which arises from nucleus-nucleus interaction, nuclear-nuclear interaction, nuclear electron interaction, electron-electron interaction. These potential. This is the general Hamiltonian for whole molecule. And it is not so simple to solve. So when we use this Hamiltonian in the Schrodinger equation, it will not be easy for us. So we use those approximations then. Now, the total wave equation, total eigenvalue equation, or total wave eigenfunction psi, and the eigenvalue E, how we write them from Schrodinger equation?
Psi equal to E psi.
E psi. Now take the first step. Assume that nuclei are fixed. When nuclei are fixed, this goes equal to this term 0. And this V and N goes out to be constant because they are fixed now. Let us suppose that I can write it as, because this is equal to 0, when we assume that the nuclei are fixed and this term remains constant, nucleus because they are fixed now, and we are left with the Hamiltonian for electronic part, the Hamiltonian for the electrons, and let that be He, sorry, and that He remains then, it is minus summation I h cut square divided by 2m, you can write I here, so for electrons we can write the Schrodinger equation He psi E is E, let me write it E dash as, and psi E to just differentiate it. This is for electrons. Now, is it okay up to here?
Yes, sir.
Yes, sir.
Okay, good. Now, the remaining part that will correspond to now nuclei. The remaining part will now correspond to nuclei, and we have an Hamiltonian for the nuclear part, and that can be represented by Hn, which is minus h cut square summation over alpha divided by 2m alpha Vnn, and total H will be now equal to He plus
H.
Hn. Now, according to Born-Opphenmier, things are now, we have to treat things now according to Born-Opphenmier. So according to Born-Opphenmier, the assumption is that, let us assume that the total eigenfunction psi for whole system means molecule, is equal to psi E psi n. This is for electron coordinates both the nuclei and the electron. Psi e, it will involve both electron and the interaction between the nuclei. And psi n is a function coordinate of nuclei only. This, because these are fixed, we are assuming that they are not varying so much. There is no variation, so they will not affect. And then equation second, sorry, not second. I can say that the total this equation. Let this, that was the first. Let I name it.
Assumption.
Yeah, let this be second. Not this. Sorry, I am doing it wrong. Not this. This is second. Total wave function. Total eigenfunction. Now second can be written as h psi n psi e psi n can be written as this e psi e psi n. So using this value, we can write now h is equal, using the value of h from first this. So we will use first now here. So when we will use first in this equation, put up the value of Hamilton, total Hamilton of the system. So we are left with, so it gives us minus alpha h cut square divided by 2m alpha. It is psi e psi n minus summation I h cut square by 2mi del square I, it is psi e psi n, plus I will write here it, so I will write it here, plus vnn plus vne plus vee into psi e psi n is e psi e psi. So this is an important equation actually. Here you will find out the different terms and the different contributions. And to solve it further, we again go to our primary approximation that nuclei are fixed. By fixed, we mean that this psi e, the wave function of the electron, it is least affected by the nuclear coordinates. It is not affected by the motion of the nucleus because nucleus is fixed. Or in other words, psi e is only a slowly varying function of the nuclear coordinates. Psi e is a slowly varying function of nuclear coordinates. So wherever if you have sometimes delta alpha square psi e.
Sir, it means
Yes.
so it means then we can separate them, electronic and nuclear.
Yeah, just listen this what I am saying. I think you will be able to understand it. Okay, so it means that wherever we have the terms del square psi e and delta alpha psi e, delta square alpha psi e, del alpha psi e. Are you seeing it? It is the
Yes, sir.
operator of the nuclei on the wave function of the electron here and here. If anywhere you find out these terms, these will be equal to 0. Neglected. You can neglect them, simply remove them. Do you understand it?
No, sir.
It means that we don't have any effect of alpha on E. Is it okay?
Yes, sir.
Okay, that is why I'm saying that if they don't have an effect, they are independent of each other, we can neglect them. This product is not then needed. In any way, this case is not present here actually. So what I can write to simplify it, I can write then delta square alpha psi e psi n can be written as, because we have already seen in the first step that we treat the nuclear wave function as a parameter, simple parameter. So I can write it as this. And also, I don't know if you have seen this expression anywhere, del square alpha. I think you should have. Anywhere? Have you used this expression anywhere? चलिए तो शायद कोई नहीं की. The reason to write this and this is that psi n has been treated as a constant. That is why we can write them like this. Otherwise, if they have been both varying functions, it was not possible for us to write like this.
सर बट साई ई तो वैरी कर रहा है ना, तो हम
Psi
इसको
e
कहाँ से
vary कर रहा
ऑपरेटर
है. Remember that.
ला सकते हैं?
Yeah, psi e is varying, but when you treat them combinedly both, because of the nucleus, it has no variation. What we mean that due to the nuclear field, psi e does not vary. That is why we are saying that psi e is a slowly varying function of nuclear coordinates, because psi n is constant.
सर वो मुझे पता है साइन कांस्टेंट रहा क्योंकि हमने फिक्स लिया. मैं साई की बात कर रही हूँ सर.
Okay, so psi e के साथ मैंने कुछ नहीं किया. Is there any problem with the psi e
सर
anywhere?
आपने ये ऑपरेटर के लेफ्ट साइड लाया है. वो होगा ना, वो विद रेस्पेक्ट टू न्यूक्लियस इंडिपेंडेंट
ये
होगा.
with
हाँ
respect to
है वो,
nucleus.
लेकिन जो ऑपरेटर है वो दोनों पे ऑपरेट करेगा, साई
That
पे
is
भी
why
साई एन पे.
this
अब
is the
देखना है
expression.
साई पे क्या होगा, साई एन पे क्या होगा. नीचे है ना वो एक्सप्रेशन जो
That is
ऊपर
why
वाला है ना.
ऊपर वाले में actually we are using these approximations in this expression. This is our main expression.
ओके सर.
Okay.
ओके सर.
Okay. Now when you use these approximations here, minus of, I can write psi e summation over alpha h cut square divided by 2m alpha two m, it can be I here. Now I can do one thing, divide each term by psi n. Divide each term by psi n. So what we can write? Minus, I can write psi e by psi n minus psi n by psi n plus psi E. Is it okay?
Yes, sir.
Yes.
Or I can write it again. Plus minus summation of I h cut square by 2m delta I square. It is psi E here plus VNE plus VE E plus psi E. There is now you can take this. See this psi. It is psi n here. I think yes, it is psi n here. This psi n by psi n is 1, so that is how this psi n is not here. Again, this psi n and psi n will go out. It will remain psi E here. This here and here. This will be going out to 1 to be 1, and this will be psi n by psi n. It will cancel out. It will be 1. This will be 1. So we are left with VNN Is it okay? Plus VNN psi E, and we have psi n psi E divided by psi n. Yes, we are okay. It is okay. Is equal to VNN psi E E psi E psi n divided by psi n. Now, this part is equal to this is E dash psi E here. This.
Yes, sir.
So that is what I have done here. And this is VNN psi E is E psi E n by psi n. Or I can write it as psi E so we can write it as it is minus psi E by psi n alpha h cut square divided by 2m alpha del alpha square psi n psi E plus VNN psi E psi E psi n psi n. If I take this psi E wait, by psi n common, what I am left with? Minus alpha h cut square by 2m alpha del square psi n. This term is okay. Plus I can write E dash psi E. I have taken psi
By
E
psi.
common, so I will write psi n by
Psi E.
psi E plus VNN. It is psi E. So psi
Psi
n
n by
by psi E. Is it okay?
Yes, sir.
is equal to E psi E into
Cyan by
psi E
cyan.
psi m. Is it okay?
Mm.
Divided by science.
ये ना
Yes,
sin.
sir. Yes, sir.
Now this part and this will cancel out.
Mm,
See this. Is
yes,
it
sir.
okay?
Yes, sir.
It gives us, I can write or minus alpha h cut square divided by 2m alpha. It is del alpha square. Sorry, here I have to it square alpha plus e dash sin cancel plus vnn sin cancel sin is equal to e psi n. This is the required result, or I can write it as in general. So we can use this is the result, or I can simply write it as is this correct?
Yes, sir.
This part is this. Yes, we can write it as actually this is separate, so vnn goes here. Okay, where is the confusion? Anybody has confusion here? I will stop here, no problem. Just tell me about what is the confusion. E is not simply the energy of the electron. E is actually energy. It is this He psi E is the it is total eigenfunction of an electron. Yes, here it is. Okay, so that is why, and this He psi, this is He actually Vne plus Vee here. If you see this equation, let me show you the equation. And this is He, and He psi E is equal to E dash psi E. Okay, so this becomes the energy of an electron. This part becomes the energy of an electron, and that is what I have written here.
सर मेरा क्वेश्चन है हमारा अगर एनर्जी ऑफ इलेक्ट्रॉन है लेकिन वेव फंक्शन हमारी न्यूक्लियस की आ रही है
वही मैं कह रहा हूँ, रिजल्ट में आ रही है ना, रिजल्ट में, इन द फाइनल रिजल्ट. Okay, let me explain it. I will explain it. So the effective Hamiltonian from here, that is what the Born-Opphenmier did actually. Effective Hamiltonian is this is the effective Hamiltonian. So what does this effective Hamiltonian actually contain? What it is? So effective Hamiltonian, just listen carefully, contains number one, it contains characteristic which I used earlier actually. Eigenfunction, eigenvalue, sorry, not eigenfunction, it's a value, eigenvalue. E dash of the electronic wave function, electronic wave equation, as part of the potential energy function for the nuclear motion. Number one. Number second is that the other part of this Hamiltonian, this function actually, that means this Hamiltonian is the nuclear interaction term VNN. So what does it mean? So I can write it as, to rearrange it, this becomes this E dash, this becomes the potential energy part for the nucleonic wave function, nuclearic motion. So it is not the kinetic energy of the electron, but this is actually the energy, that characteristic eigenvalue of the electronic wave function, and it acts as a potential energy function for nuclear motion. And the second term, this VNN, this becomes the nuclear interaction. So we have included all in this. By assuming that they are fixed, even we can find that we can use this nuclear interaction term by using the Born-Opphenmier approximation. Thus we can say that Born-Opphenmier approximation, it helps us to solve the complete molecular wave equation. How? Number one, the electronic state of a molecule, electronic state, that means the contribution from the electrons, is solved just see this Hamiltonian. I am repeating this effective Hamiltonian. This becomes the kinetic energy part for the nucleus. This is a nuclear interaction. This is the combined Hamiltonian. This does not correspond to any particular electron contribution or the nuclear contribution. It is a contribution as a whole of the molecule. So we are calculating the Hamiltonian for whole molecule. That is why it is called effective Hamiltonian. It contains a contribution of both electrons as well as nuclei. So this becomes the kinetic energy part of the nuclei. This becomes the potential energy part for the nuclei. That means the energy eigenvalue of the electronic wave equation that acts as a potential energy for nuclear motion. So all the electrons will create a potential which will affect the nuclear motion. That is what this E dash means. Now VNN, this VNN becomes the potential of nuclear-nucleonic term, nuclear interaction. So it includes both the interaction, the electronic part, the nuclear interaction part. Okay. So from this, we can conclude that the wave equation, which is He psi E equal to E dash psi E, this wave equation for a given electronic state of the molecule, that means for given electronic states, all the states of all the electrons combinedly, we solve this for a range of nuclear coordinates. So we can solve this by using this equation here, E dash. So we take the E dash and find it, put up in this equation, So we solve the equation, actually total equation then. So once we obtain the EE dash, then we can solve the nuclear wave equation, as I said, by putting in it here. This gives an expression, then we can find, then we have psi n and E, total E, whole molecule in the given electronic state, in the effective state of the electrons, whole electrons, all the electrons. So for each electronic state, and remember that we have to find psi n and E for each electronic state. That means when the electronic states, different electronic states are there in a molecule. So for each electronic state, we have to solve like psi 100, psi 200, psi 210. That is what we mean electronic states here. Then the complete wave function psi, it is written as product of psi E into psi n. I will repeat it again. Electronic wave function for any given electronic state in a molecule, that means in a molecule has different electronic states. So this, the electronic wave equation, that is He psi E equal to E dash psi E, it is solved for a particular given set of electronic states in a given molecule using those nuclear coordinates, because those are slowly varying functions, so it will not affect our electronic energy part. Then we find psi E and E dash. So here we find psi E and E dash. Sorry. So once we find psi E and E dash, then we use this E dash in the effective Hamiltonian here. When you solve this effective Hamiltonian using this value psi E and E dash, what you find, you will find psi n and total E. This E is for a whole molecule. Psi E you have already found, psi n you are finding from this effective Hamiltonian, and E you will get from the effective Hamiltonian. So you have almost all the parameters for the whole molecule in a given electronic state. For a given electronic state. So in this way, we solve these set for each electronic state to get psi n and psi E, nuclear wave function and total energy. And then we take the total wave function psi equal to psi E, product of psi E and psi. In this way, we are able to solve the Schrodinger equation for a molecule. Just try to understand. If you have written in somewhere, and I will send you the video recording, try to understand what I am saying. And assume that you have a given set of atoms to form a molecule, and we assume that nucleus is slowly varying, so it does not affect whole on electron, but electrons will affect the nucleus. Reverse, it's not reverse actually. So in this way, this Opphenmier approximation is complete, and I have already told you that there are different types of molecular spectra. It may be electronic spectra, it is vibrational rotational spectra, it is pure rotational spectra. And electronic spectra, it has an energy range of few electron volts. The vibrational rotational spectra, they are near approximate range is 1 micron to 10, this is for 2 micrometers actually. 1 micron is equal to 10, is wavelength, which is 10 to the power 4 angstrom. And it falls in the range of IR, near IR, NIR, near infrared. And remember that, like in this atomic spectra, what we observe in the spectrum, we either observe a line spectra, but here in this case, we can observe both the absorption as well as the emission, but not the lines, we observe bands, set of lines So there is in molecular spectra acts, this is observed as bands. So absorption band, emission band in this case in the molecules. And this vibrational rotational is observed in these vibrational rotational spectra is only observed for heteronuclear molecules. Heteronuclear molecules. So it is only observed for heteronuclear molecules. So homonuclear do not produce vibrational rotational spectra. And this is a pure rotational spectra. That means rotational spectra. It goes into far IR, far infrared, and it 10 is power 2 micron to 10 is power 3 micron in this energy range, or in the microwave range. Microwave range, it goes in 10 is power 3 to 10 is power 4 micron. Each spectrum then has a equidistant lines actually, and we will study them separately for the diatomic molecules, and hopefully in the next class. Okay.